Do you know your phone has GPS? Yes, I know you know it. But I think you don't know your phone has GLONASS also. Your phone has chipset for Baidu also. Your phone has Galileo also. Well, myself Aninda and I am here to help you. Your phone receives the satellite signal which is coming from the space, and after filtering analyzes it using the navigation processor and gives you the output. What is the output here? The location of your device is the output. Your phone has lot of apps including Google Maps that uses the location of your device. In this video I will show you how to collect the raw data which is coming from the satellite, and I will show you how to analyze this using the MATLAB. So a lot of information is there. Up to this you all know, but to understand the data, raw data, you should have some basic knowledge. So I have decided to make this video in two parts, part 1 and part 2. You are watching the part 1 and part 2 will come in 2 or 3 days. So in part 1 I have discussed some basic knowledge. So do not skip this video. If you skip this video you will not understand the second part. So please watch this video up till the end. This video is a little bit theoretical, but I will try to describe it in a very pictorial way. And the second thing I want to say that in this video I will discuss all that things very basic, in very basic way. So if you want to, after watching this video, if you want to know some details about this any terms, so write comment in the comment section. I will elaborate. I will bring a new video and elaborate in that video. So comment in the comment section.
Okay guys, I have made this PPT to discuss all the basic concepts, and I think it will help you to know all this concept easily. And if you want this PPT, tell me in the comment section, I will send you. So let's start. First, you have to know what is navigation. According to Oxford Dictionary, navigation is any of several methods of determining or planning a ship's or a aircraft's position and course by geometry, astronomy, radio signal, etc. It is a little bit confusing, but don't worry, forget about it. In a very simpler way, navigation is a technique to determine the position and velocity of any object or any vehicle on the Earth's surface. And not only the position and velocity, but also the attitude, acceleration, and angular velocity also. And there are two fundamental methods for navigation techniques. One is position fixing method, and the second one is date reckoning method. So first I will discuss about date reckoning, and then I will discuss this position fixing. So in case of date reckoning, first just think there is a moving car, and you know the initial position of this car, and this car has installed speedometer, gyroscope, accelerometer sensor, and you are calculating the current position of this car by using the previous position of this car and those sensor data. So in this case, the sensor errors will be getting added over time. So that is the main disadvantage of this date reckoning method. Let's see position fixing. Position fixing is nothing but basically determining the position of a vehicle or a person on the surface of the earth. So there are few processes or few methods for position fixing. So we'll know. There are few position fixing techniques are there. So first one is bearing. So first we will consider 2 dimension. Later we will know about 3 dimension. So in case of bearing, suppose you want to know the position of x. For this, a known point is required. In this case, the position of A is known. Suppose the position of A is known, and this is a not direction. So you can say the position of x by this much angle in clockwise direction. And if you know the position of B, you can say the position of x by this much angle in anti-clockwise direction. So this is bearing. And next is ranging. Ranging is basically that measuring the distance between 2 points. So here you want to know the position of x, and for this the position of A is known. So if we measure the distance between A and x, then we can't say the exact position of x, because the distance between A and anywhere on this circle is same, because this is the radius. So if we include one more known point, suppose the position of B is known. So in this case, we can't say the exact position of x. X may be at x1 and x may be at x2, because the distance between A and x1 and A and x2 are same, and the distance between x1 and B and x2 and B are same. So we can't conclude. So if we include one more known point, then we can say that the exact position of x. Now think this A, B, C as a satellite. Then the satellite transmits the signal and the receiver receives the signal, and then receiver calculates the distance between the A and this means the satellite and the receiver. So in case of 2D, if you want to fix or if you want to determine any position, then you need minimum 3 number of satellites. Now in case of 3D, instead of circle you will get sphere, and consider assume the satellite at the center of the sphere. And if two spheres cut each other, we will get a circle, and the distance between anywhere on the circle and the satellite is same. So we can't compute the exact position of this using these two satellites. So if we include one more satellite, we will get 2 points. See, in case of 2D, if you use one satellite, we will get a circle. If we use two satellites, we will get 2 points, and if we use 3 satellites, we will get the fixed one position, exact position. And in case of 3D, if we use one circle, if we use one satellite, we will get a sphere. If we use 2 satellites, we will get a circle, and if we get 3 satellites, we will get 2 points. So we need one more satellite in case of 3D to determine the exact position. So that is, so we need minimum 4 number of satellites to determine the exact position of any object anywhere on the surface of the Earth. So this image is for visualization purpose. You can visualize this is the Earth and a car is there. So we need minimum 4 number of satellites to determine or to fix any position of a vehicle or any object on the surface of the Earth. So there are different types of navigation systems. So first one, the radio navigation system. Second one is the inertial navigation system. Third one is the satellite navigation system. So in this video, I will discuss about the satellite navigation system. But next 2 slides, I will give you the brief idea about these 2 type of navigation system. So first one is the radio navigation system. First radio navigation system were used in 1930, and there are 7 basic techniques for radio navigation. First one is maker beacons, directional finding, bearing and elevation, passive ranging, two-way ranging, hyperbolic ranging, and Doppler ranging. And I am not discussing these things. If you want to know about, suppose if you want to know about Doppler positioning system or any other, or if you want to know any other topic, so tell me in the comment section. I will bring a new video. This radio navigation system do not gives out the same coverage area, do not offer the same accuracy as the GNSS does. GNSS is basically the global navigation satellite system, and this radio navigation system basically uses a backup for this global navigation satellite system. Inertial navigation system is nothing but a date reckoning system. So as I discussed before about date recording, in case of date recording and sensors are required, gyroscope, accelerometer, sensor. For this inertial measurement unit is there. It will be clear in this image. So see here, IMU is there. IMU is basically the inertial measurement unit, and see sensor are there, gyroscope sensor and accelerometer sensor. And this initial condition is required. Then and the navigation process these 2 things: initial condition, and mainly the previous position, and the sensor data, and then gives you the output, the position, velocity, altitude, and etc. As I discussed before, in case of date recording, the sensor errors will getting added over time. So this is the main disadvantage of this date recording as well as the inertial navigation system. So if you watch any live launch of ISRO, you can see this kind of display. At the corner, you can see T and I is there. T is basically the tracking data is denoted by this yellow line, and I is basically the inertial navigation system is denoted by this green line. Basically, we are getting the data from inertial navigation system which is installed inside the rocket, and this red line is predicted path of the rocket. And for your interest, I want to say that here it is written HSS. HSS is basically a heat shield separation. There are 2 fairings at the top of the rocket, basically act as a heat shield for the satellite or vehicle which is inside the rocket. And here is written that L11D on, basically main engine is on here. At the time of launch, only 2 side boosters are ignited, and after a few seconds, the main engine is ignited. And this is one more display. Here it is clearly written INS, basically the inertial navigation system. denoted by this green line, and we are plotting this graph depending on the data which is given by the National Navigation System. And here it is written that C2S on, basically second stage is on here, and C2S off, basically second step is off here, and SAT SCP, satellite separation is performed here. My satellite is separated from the rocket. And next is the satellite navigation system. Satellite navigation system, basically the GNSS, Global Navigation Satellite System, is a collective term for those navigation system that which provides us the three-dimensional positioning solution on the surface of the Earth. And there are few navigation systems are there which gives us global coverage. First one is GPS, operated by USA. Second one is GLONASS, operated by Russia. Third one is Galileo, operated by European Union. Fourth one is Baidu, operated by China. These all four navigation system gives us global coverage, that covers the whole Earth. And you know that your phone has GPS, but believe me, your phone has all these navigation system. Your phone has chipset for navigation. Your phone has navigation processor for all these navigation system. And I will give you proof in the next part of this video. Wait for the part 2 for second part of this video. And few navigation systems are local, gives us local coverage. QZS, operated by Japan, gives us local coverage of the South Asia, and IRNSS, operated by India, this also gives us local coverage. GNSS architecture. So GNSS has three main components. One is a space segment, and second one is the control segment, basically the ground station, the monitoring station, and third one is a user segment. User segment is basically we are the user. So I will discuss these three next slide. So before discussing those three, you should know about LEO, MEO, and GEO. LEO basically the lower Earth orbit, MEO basically the medium Earth orbit, and GEO basically geosynchronous Earth orbit. In the next slide, it will be clear. Here you can see LEO, the altitude range is 160 to 2000 kilometers. And the period is 88 to 127 minutes. Basically, the satellite which is placed at the LEO will take 88 to 127 minutes to complete one rotation around the Earth. And the altitude of the MEO is 10,000 to 20,000 kilometers, and period is 2 to 12 hours. And the altitude for GEO is 35,786 kilometers, and the period is 24 hours. And the rotation of Earth across its axis is 24 hours. So the satellite which is placed at GEO remains stationary with respect to Earth. Here you can see the satellite which is placed at LEO gives you the smaller coverage than the satellite which is placed at MEO. MEO gives a large, and the satellite which is placed at GEO will gives you more coverage. If you want to cover the whole Earth, you need large number of satellites. If you place the satellite in the LEO, and if you want to cover the whole Earth, and if you place the satellite in the MEO, you will require less number of satellites with compared to the LEO. So basically, the GPS satellite are placed at MEO, and the military satellite are placed at LEO, and basically the broadcasting TV or communication satellites are placed at GEO. And there is a little bit difference between geosynchronous orbit and geostationary orbits. Both the orbit are placed at the about approx 36,000 kilometers above from the Earth's surface, but the geostationary orbit is placed at the equatorial plane, and geosynchronous orbit is placed at some angle of inclination with respect to the equatorial plane. Period for both the orbit is 23 hours 56 minutes, basically 4 hours. And the next one is GNSS space segment. Space segment is basically nothing but a group of satellites, or a constellation of satellites which is placed in space. And the next one is GNSS control segment. Control segment is basically the ground station. You can see there are three parts in the control segment: monitoring station, control station, and uplink station. Monitoring station has antenna, and the antenna receives the satellite signal and sends those data to the control segment, control station. Control station analyzes those data, and if any maneuver occurs or any update occurs, then the control station sends those data to the satellite by using the uplink station. The main funda of the uplink station is to upload those data to the satellite. And the third one is GNSS user segment. Basically, we are the user. Suppose you have the cell phone. Your cell phone has antenna that receives this radio signal and converts the signal to electrical signal. And the ranging processor processes the distance between, basically the range distance between satellite and your cell phone. And then the navigation processor processes all those data and gives you the output as a position, velocity, etc. And the error due to clock is also compensated by this navigation processor. We will know what is the clock error in next. So next one is the clock frequency drift. If you have a clock and you have synchronized this clock with respect to a reference clock, then also it will gradually desynchronize with respect to this reference clock as the time elapsed. According to the relativity theory of the Einstein, the time dilution is one of the reason for clock drift. The clock which is placed at the strong gravitational field will run slowly, and the clock which is placed at the weaker gravitational field will run faster. And the GPS satellites are placed at the MEO, medium Earth orbit. So those satellites, the clock of these satellites placed at the weaker gravitational field, because the gravitational field is weaker at MEO with respect to this Earth surface. So if we do not consider this relativity theory, the navigation system which is based on the GPS will falls after only 2 minutes. If we do not consider this, if for every day it will give you the error up to 10 kilometers. It's a huge error. So the second one is the clock bias. So in cell phone we have the quartz clock, and atomic clock is used in satellite. So we know the atomic clock is the more accurate clock. So clock bias is basically the error, time error. And this bias is basically the difference between the receiver clock and satellite clock. Even though this error may be in millisecond range, but also it will gives you the large error in position, because we know the distance equal to the velocity and the time. So the velocity of the radio signal is same of velocity of light. So it will give you the large number of position error if you even though the time error is in millisecond and nanosecond range. So it is a big fact. So there is a time delay between the hardware. So suppose satellite clock is there, so there is a hardware time delay between satellite clock and the time of emission of the signal, and there is also another hardware time delay between the receiving the signal and the receiver clock. So this delay is also known as bias. Basically, bias is the error, time error. So next one is the pseudo range. Pseudo range is basically the pseudo distance between satellite and the receiver, and basically major range is called pseudo range, and that actual distance between satellite and the receiver antenna is called true range. And the pseudo range is not equal to true range because the due to clock error and other physical error is there. Pseudo range is basically the distance, measured distance. So measured distance is not equal to true distance. The receiver clock and satellite clocks are not synchronized, because in satellite atomic clocks are used and in receiver quartz clock is there. So if the receiver clock is running ahead of the satellite clock, then the measured time of arrival of the signal is later than the actual time of arrival. That causes the overestimated range measurement. And if the satellite clock is running ahead of the receiver clock, then the actual time of transmission will be the earlier than the intended time of transmission. So in this case, it will cause the underestimated range measurement. So next one is range errors. Despite our best efforts, there will be range errors due to some other facts. So let's see those facts. So first one is the satellite ephemeris error. Basically, we are assuming the satellite is placed at that orbit, basically denoted by this solid line, but due to some error, satellite is shifted from its actual orbit to this orbit denoted by this dotted line. And we know the position fixing method is dependent on the ranging, and we calculate the range from a known point. So if the known point is satellite point, so if the known point is shifted from its actual point to another point, so we will get error in range. Second type is receiver error. Receiver error occurs due to some electrical noise or any computational error in receiver. So you will get error in pseudo range measurement. The third one is the atmospheric propagation error. As we all know, the light rays bend when it passing through a prism. At the same way, the radio signal bends when it is passing through the atmospheric ionosphere. So the fourth one is the multipath error. Here you can say this plane is getting signal from the satellite, directly satellite, and other signal which is reflected by this mountain. So that is called the multipath error. So next one is the sky plot. That is one of the most important thing. So from this image you can understand the satellite signal can be blocked by the buildings, trees and mountains. So those satellite has higher elevation, and then the probability of the signal blocked by the buildings or trees will be less. So sky plot is basically the visual or graphical screen aids for identifying when the satellites are being masked by the surroundings, trees or buildings or mountains. This is the Earth and you are at this point. So the satellite placed here, the elevation is 0 and the satellite placed at the top of your head, the elevation is 90 degree. So those satellites are located beyond this 30 degree. So there is a more probability that the signals of those satellites may be blocked by this building and trees, mountain, etc. And azimuth is basically the horizontal angle in degrees measured in clockwise. And basically this is the sky plot. This is the graphical plot. It's called the sky plot. Here you can see the azimuth angle. The elevation angle from 0 degree to 90 degree, and 90 degree is the top of your head. So after beyond this 30 degree, we will not consider those satellites. So we should consider the satellite is inside this 30 degree circle. And this is the azimuth angle: 30 degree, 0 degree, 30 degree, 60 degree, 90 degree in clockwise direction. The azimuth angle is horizontal angle from 0 degree to 360 degree. So in this sky plot, you can visualize the movement of those satellites in the sky plot. So you can see this is the sky plot, and you can see the movement of the satellites. So next one is the carrier to noise density. It is denoted by C by N naught. So carrier to noise density is the ratio of the received signal power to the noise density. So higher C by N naught result in reduced data bit error. So the higher elevation satellite will give you higher C by N naught. The lower elevation satellite will give you lower C by N naught, because the noise density will be high for lower elevation satellite. And this C by N naught is denoted by decibel. So if PC is the received signal power and PN is the noise power, then this carrier to noise ratio is at 10 log 10 PC by PN in decibels. But this carrier to noise ratio is not same with the signal to noise ratio, because when we calculate the carrier to noise ratio, we assume that noise has infinite bandwidth. And when we calculate the signal to noise ratio, we calculate in a certain bandwidth of noise.
So up to this, all the conceptual things are over.
And next 2 or 3 4 slides I will give you some basic information just, and then I will conclude this video. So in case of GPS, GPS has 31 operational satellites in the orbit, and among them USA tries to maintain at least for 24 satellites, because GPS satellites are placed at MEO and it requires 24 million satellites to cover the whole world. These 24 satellites are placed at 6 different orbit. 1, 2, 3, 4, 5, 6, 6 different orbit. 24 satellites are placed in 6 different orbits. From this place, from this blue colored place, from every place the visible satellite is 8, 9, 10, 9. So the Earth is rotating, and this is the satellites are rotating in the orbit. In 3D, minimum 4 number of satellites are required to determine any position. So in this case, we can say visible GPS satellite from every place. This blue color is rotating, and you can say for different place the visible satellite. So it is more than 4, so it's okay. And this is basically the control segment of GPS. You can say the control segment of GPS. Here you can see the green triangle is denoted by ground antenna. So you can say the ground antenna of GPS is located for ground station for this control segment. So next one is GLONASS. GLONASS is operated by Russia. So in 2010, GLONASS has achieved full coverage in Russian territory, and in October 2011, in just within 1 year, GLONASS offers us the whole global coverage, and they complete the 24 satellites. Because if you placed in the MEO, then you require 24 satellites to cover the whole Earth. And GLONASS has probably the similar level of accuracy to GPS, and the more advantage if you use the GLONASS and GPS together, you will get the better accuracy and you will get your location very quickly. Galileo is supported by European Union, and it also offers us global coverage like GPS and GLONASS. And Galileo has 26 satellites in the orbit, and they expect that by 2020 they will complete a constellation of 30 satellites. And the satellite of this Galileo is orbiting 23,222 kilometer above from the Earth's surface with medium Earth orbit. So next one is the Boidu, is operated by China. So Boidu has two separate constellations, Boidu 1 and Boidu 2. Boidu 1 is the first generation constellation, has 3 satellites, and Boidu 2 has second generation constellation, is also known as Compass. So Boidu 1 was decommissioned at the end of 2012. And the second generation navigation system, basically the Boidu 2, is also known as Boidu navigation satellite system, and it offers the coverage in Asia Pacific region. So China in 2015, China launched this third generation Boidu system for global coverage. So now China has 35 satellites in the orbit for this navigation purpose. So this is QZS, operated by Japan, is also known as Michibiki. It has 4 satellites and gives you the local coverage, regional coverage. And Japan is trying to increase up to 7 satellites by 2023. And here you can see these 4 satellites are orbiting in 4 different orbit. And this QZS helps GPS to give the better accuracy in this Asia Pacific region, South Asia Pacific region. And this is our regional navigation satellite system. Our means our Indian, and basically operational name is NAVIC, navigation with Indian constellation. Here you can see the coverage area of NAVIC. It gives a local coverage up to 1,500 km beyond the border of India, and it has 7 constellation satellites in the space segment, and 3 of them are placed in the geostationary orbit, and remaining 4 are placed at the geosynchronous orbit. Here you can see this blue, red, and pink orbits are geosynchronous orbit because it has an inclination with respect to this equatorial plane, and this green and this orange orbits are geostationary orbit. This is the second last slide. I have included just for information purpose. On 10 February 2009, 2 Russian communication satellites, Iridium-33 and Cosmos 2251, accidentally collided at the speed of 11,700 meters per second at an altitude of 789 kilometers. Here you can see the orbit of Cosmos, and here you can see the orbit of Iridium-33, and they collided here. In this peak you can see the latitude and longitude is given and at the collision spot, and due to this collision a lot of space debris were formed. So what is a space debris? So space debris are basically the space junk, space pollution, space waste, space garbage are created by this non-functional spacecraft and created by the dead satellites and the failed mission, created by some failed missions, the rocket with the few rocket parts created the space junk, but not only created by the human but also created by the solar storms also. So before ending this video, I have a question for you. What is the difference between position and location? So if you know the answer, then write in the comment section, and if you don't know the answer, then you can also write in the comment section your views or your assumption.
Guys, if you want this PPT, please write down your email ID in the comment section. I will send you, or my email ID is given in the description below. You can mail me. I will send you the base PPT. And if you like this video, like it, and if you like this channel, subscribe this channel, and please press the bell icon, because the main part of this video, a second part, will come within 2 or 3 days, so you will get the notification. And so once again, if you want to share it. So thanks for watching.